Today, we'll dive into numerical algorithms, the backbone of computational problem solving. From finding roots to solving equations, these methods help us approximate answers where exact solutions aren't possible. Think of how Google Maps calculates shortest distance, or scientific software computes integrals. All rely on numerical algorithms. So numerical algorithms is equal to step-by-step methods to solve mathematical problems approximately using finite steps. Some examples of this are root finding, Newton-Raphson, solving equations of linear algebra, Gauss elimination, and numerical integration, which is basically the trapezoidal rule or Simpson's rule. So for x is equal to root 2, we have root 2, which is equal to root 2 minus, and let's say f of x is x square minus 2 upon f dash of x would be basically 2x, right? So this is what our solution would look like, which basically is a quadratic equation. So the next topic is solving linear systems with Gauss elimination. So suppose we want to solve, two equations, right? So for example, x plus y is equal to 2 and x minus y is equal to 0 dash. How would we do this, right? So now let's say you want to solve three equations, which is basically a linear system. How would we do this? So firstly, let's say we have 2x plus 3y minus z is equal to 5. We have x minus 2y plus 4z is equal to minus 2. Then we have 3x plus y plus 2z is equal to 7. So now our augmented matrix would look like somewhat like this. So it will basically be 2, 3, minus 1. And we have a 5 over here, right? And so similarly, what we can do is for the rest ones, we can do my 1 minus 2, 4, and then minus 2, right? Then we have 3, 1, 2, and 7. So I hope this is clear. This is basically what we call as the augmented matrix. And this we get basically by taking the coefficients here, right? These coefficients are plugged in, and these final values on the right hand side are these values over here. So I hope this is clear. Now performing the row operations here, what do we get? So let's say firstly we multiply the middle row with 3 on both sides. So we get something like this. So we get 2, 3, minus 1, 5, right? We then get 3, minus 6, 12, and minus 6. Then we have 3, 1, 2, and 7. So this would basically give us, and after this, let's say we want to subtract these two rows. So the way we do this is the first row remains unchanged. So it will be 2, 3, minus 1, and then 5. Then we have, so 3 minus 3 is 0. Minus 6 minus 1 is minus 7. Then we have 12 minus 2, which is 10. Then we have minus 6 minus 7 is minus 13, right? Then we have 3, 1, 2, and 7 here. So after all the operations, what we get as the final augmented matrix is somewhat like this. 1 minus 2, 4, minus 2, 0, 7, 9, 0, 7 minus 10, 9, 13, right? So solving for XYZ using back substitution. So using back substitution, we can solve for XYZ over here. So if you calculate, you'll find out that X is equal to 1, Y is equal to 2, and Z is equal to 1. This is going to be your final answer. Next, we have the numerical integration example. So here we first have the trapezoidal. So trapezoidal rule is something like this. Say we have this graph. And we have something like this. Just say we have this graph. And we have these data points. So now what we get is something like this, right? So the area under the curve would basically be the sum of all the trapezoids. So these are the trapezoids. So the area under the sum would be the sum of all these trapezoids right here. So trapezoidal rule is essentially a very simple way for approximating the definite integral of a function, right? So if this is a function, f of x, right? So if this is a function, then summing all the trapezoids would give us the area. So basically what this means mathematically is summation or integration of f of x dx would basically be h by 2 or half of height into f x0 plus 2 fx1 plus fx2 plus fxn minus 1 plus fxn so this is how it would look like. By the way, why did the mathematician use a numerical method? Because he wanted to get to the root of the matter, approximately. What do you call a numerical algorithm that's always stuck? A fixed point iteration. Get it? So in error and convergence, the next topic, we have two main key points. Right? So firstly, we have truncation error. And next we have the round off error. Truncation error is from approximation. And then we have the round off error, which is from machine precision. So to recap, Newton-Raphson roots. Then we have Gauss elimination. This linear systems. Then we have trapezoidal integration. So here we can have a mini task. Solve f of x is equal to cos x minus x with Newton-Raphson. Apply Gauss elimination 3 cross 3 system and approximate integral of sin x, approximate integral 0 to 1 sin of x dx using trapezoidal rule for n is equal to 4.